So what we get is it says, gives us a figure. So we have an ideal battery. We have a switch. I have a branch here. And so this is marked as resistor 1. There's our inductor. Resistor 2 and the inductor. It says the battery is ideal and the voltage is just 10 volts. Okay. It says resistor 1 is 5 ohms. It says resistor 2 is 10 ohms. It says that the inductor is 5 henries. Okay. It says the switch S is closed at time t equals 0. Okay. Just afterwards, what are the current through each resistor and the current through the switch, the potential difference across the resistors, and the potential difference across the inductor? And so we'll immediately after the switch is closed, then what we're going to calculate are these various values. Okay, and so we want the current through resistor 1, the current through resistor 2, the current through the inductor, and then we want our voltages. So then I want the voltage across resistor 1, the voltage across resistor 2, and then the voltage across the inductor. Okay. All right. So then, what we're going to do is we're going to look at some loop rules. Okay. So in this first loop, we go up by the voltage on the battery, and then down by the voltage across resistor 1 goes to 0. So that tells me that the voltage across resistor 1 is just going to be what? If we go up by 10, then we have to go down by what on resistor 1? How much?
It's 5 ohms, right?
Yeah, it is 5 ohms, but what's the voltage? 10. Okay, so it's got to be 10 volts. By the loop rule. Okay. Now, if you know the voltage on resistor 1, and it is 5 ohms, like you pointed out, then what's the current in resistor 1? Five ohms. Yeah. This is by, Ohm's law. We got the voltage, we know the resistance, we should get the current. Are we good? All right, now, if we look at loop 2, then we go up by the voltage on the battery. We will go down by the voltage across the inductor, and then down by the voltage across resistor 2, has to add to 0. So then what you get is that these two voltages have to add back up to our 10 volts. Okay. But now what you're going to talk about is the guiding principle. The current through the inductor can only change continuously. And before we close the switch, what was the current in that inductor? 0. After you close the switch, immediately after, the current has to still be what?
0.
is by the guiding principle. Well, if there's no current in the inductor, what's the current in the resistor?
Oh, wait, that's 10, 1 amp.
So
Oh, sorry, I'm looking at that.
that's all right. So if there's no current here, what's the current in resistor 2?
0.
Yeah. Because why?
Because, like you said, it has to be constant. And since the inductor has 0, then didn't reach the resistor.
Yeah. They're in series. Elements in series have the same current. They have to. So if there's no current in the inductor, there's no current in the resistor. Well, if there's no current in the resistor, what's the voltage on resistor 2? 0. Well, if there's no voltage here, when we do our loop rule, what's the voltage on the inductor have to be? Yeah, if you go up by 10, down by something, and down by nothing, the 10 had to be there. So this has got to be 10 volts. We didn't use this angle formula. We use basic concepts in circuits. It's kind of like a conceptual circuit question. Okay? All right, now, after the switch is closed for a long time, repeat all the questions. Well, did anything change for resistor 1 from initially closing the switch to the switch being closed for a long time? No. No, those just stay the same. So this is, 2 amps, and then our voltage across resistor 1 is the 10 volts. And again, that's a loop rule, that's Ohm's law, it didn't change at all. But once we establish the current in the inductor, because the Faraday's law, the induced voltage will fight the current, but it will always lose. So we will eventually establish current and reach a constant current value. Then what is our voltage across the inductor? Once the current is constant. In the inductor, then the voltage here is Faraday's law, right? Minus L di dt. Well, what's it going to be? Well, what's this going to be? Since this is that, once the current's constant, what do we get for a voltage across the inductor?
10. No,
What's the derivative of a constant?
0.
What's your voltage on the inductor?
0.
It does nothing. It just lets the current go because the current isn't changing. If there's no changing current, there's no changing magnetic field, there's no changing flux, there's no nothing. If the flux is constant, because the current is constant, because the magnetic field is constant, there's no induced anything's going on. So this is 0. Are we good? Well, that's 0. Then when you loop it, what's the voltage across the resistor 2? 10. Okay. Well, if you got 10 volts on resistor 2, what's our current in resistor 2 going to be?
1.
Ohm's law. If you got 1 amp in resistor 2, what's the current in the inductor? 1. Because they're in series. That's what our current 1 has. Whatever current resistor 2 has is the current in the inductor. Are we good? All right. Once again, no real formulas for us. But now, after we establish this current, 1 amp in the inductor heading down, we're going to open the switch again. And the question is, immediately after you reopen the switch, what are all the same things? So, when you open the switch, battery's no longer attached. We had 1 amp heading down. So, after you open the switch, immediately afterwards, what are all the same things? Well, what we start with is that by the guiding principle, the current in the inductor can only change continuously. And when the switch was closed, the current in the inductor was what? 1, heading down. Once you pop the switch open, it has to be what?
Right, immediately 1.
1 amp heading down. And this is essentially by the principle. Well, if you got 1 amp in that inductor, what's the current in your resistor 2? What's your current in resistor 1? Notice that when the switch was closed, the current in resistor 1 was what? 2 down. When you pop it open, it goes from 2 down to 1 up immediately. But that's okay. It's a resistor. Resistors can do that. Inductors cannot. Okay? So, these are both by series. And the thing you need to note is that this one instantly reverse direction. Okay. Now, we know the currents in resistor 1 and resistor 2. What are the voltages going to be? What's voltage for resistor 1? Volts by Ohm's law. What's the voltage in resistor 2? Now this is the coolest thing about the problem. We're going to loop it by our loop rule. Energy is going to be supplied by the inductor. So I'm going to write this as plus voltage on the inductor. Minus energy is being removed by the resistor because it gets hot. Voltage across resistor 2. Voltage across resistor 1 because we're looping in the direction of the currents. 0. So the removal of the energy by the resistors has to be equal to the energy being supplied by the inductor. What's the voltage? 15. More than the battery. Why? Because that current cannot change discontinuously, or dIdt is not defined. And you get an infinite answer for your voltage. And that is not possible. It's not physical. So, only change continuously. To maintain that 1 amp current going down, then to oppose the change in current as it tries to go down, you will then supply 15 volts worth of induced EMF in the inductor. Questions?